Welcome, physics family. We're going to talk about electromagnetic induction today. To do so, we're going to start off with Michael Faraday and Joseph Henry. These are two physicists that were working on the same idea at the same time, though Michael Faraday gets credit for electromagnetic induction. And basically what electromagnetic induction is that you actually can create voltage by simply moving a magnet in and out of a coiled wire. Now, if you go to this YouTube link, which is in Canvas as well, or take a look at it, it'll show you that simply putting a magnet in and out of a coiled wire will create voltage. Here's an example. So here's the bar magnet, and if you're pushing it in and out, in and out, in and out of the coil, by simply doing that, you actually start to create a voltage, which leads to a current. So either the coil or the magnet have to be moving, but they have to move past each other. And the more loops that the coil has, the greater the induced voltage there is. So the more you're moving it and the more coils, the more voltage you are going to create, which means you're going to create more current. So electromagnetic induction basically means that by moving the magnet in and out of the coil, you create voltage, which makes current. We know as voltage goes up, so does the current, right? And we know that's with Ohm's law, V equals IR. So as voltage increases, so does the current. Now, when we create a current, we know that anything with a current becomes an electromagnet because it has a magnetic field. And that magnetic field in those coils start to repel the magnetic field of the bar magnet, strangely enough. All right, and how fast you move the magnet in and out of the coil actually affects how much voltage is induced. The more in and out, in and out, in and out you go, the more voltage there is. So Faraday's law, to wrap everything up, is if you want to induce voltage and you want it to get larger, just increase the number of loops. We note that with the letter N for number of loops. Or increase the rate at which the magnetic field changes, meaning move it in and out faster. The faster you move it, the greater the induced voltage will be. Now, as we kind of already know from Ohm's law, if you want to know how much current's going to be produced, well, we know that depends on the voltage, but also the resistance of the metal of the coil. So take something like a coil of copper wire, which is a really good conductor, and you take something like iron that can conduct, but not as well. Since the resistance is higher in the iron and lower in the copper, we know then that the current would be higher here, and the current would be lower here in the iron. So that just has to do more with Ohm's law, but the idea that if you want more current, we've got to induce more voltage. Mathematically, Faraday's idea is represented in this equation right here. You're already familiar with the V, which is voltage, measured in volts. The N is something new, right? N is just the number of loops in the coil. So if you're dealing with something like the rim of a wheel, that's just one loop. If you're dealing with a big coil of copper that has 3,000 loops in it, so be it. Then the number is 3,000, but that is what letter N stands for. A is simple, that's area, measured in meters squared, all right? And since we're dealing a lot with loops and circles, don't forget that the area of a circle is indeed pi r squared. So keep that in mind. And if you have anything like the radius, right, and it's in centimeters, make sure you convert it to meters first before you plug it into the equation. Magnetic field is the variable B. We're already used to that. That's measured in T, which is Tesla. And then last but not least is the time. When you divide by the time, you're really talking about the rate at which the change in the magnetic field is happening, and that's in seconds. So, if we think about the relationships that Faraday's law spoke of in the previous slide, if you increase the number of loops, algebraically, the voltage should increase as well. If you increase the time, which means that the rate slows down because it's going slower, that means your voltage should decrease. Vice versa, if you make it faster so the rate is shorter in time, less time gives you more induced voltage. So Faraday's law holds true. The concepts and the math coincide very well. if you want to recap real quick, Faraday said that moving the loops of wire near a magnet is going to create voltage, or moving a magnet near the loop of wire, or vice versa, either one will create voltage, which can create current. Also, one that we don't focus on too much, but that is true, if you change the current in the loop, you change the magnetic field. And by changing the magnetic field, you can induce voltage on other objects as well. So it's all about this changing and moving that's going to create voltage. Now, where does Faraday's law hold true in real life? Well, first of all, if you've ever been at a red light late at night and it turns green really fast when you pull up, that has to do with traffic light triggers, which tend to be underneath the car. Your car is a piece of metal, and by driving over this sensor, the movement of the metal creates a disturbance in the magnetic field. That disturbance in the magnetic field, of course, is going to induce a voltage, which is going to be felt by the current change in the machine or instrument, which is going to trigger the idea that, oh, something is above this object, so it must be a car waiting to turn. So by having that moving metal, you're inducing a voltage, which is going to create some kind of read in the machine to let it know, oh, let's switch the lights. Hybrid cars are very important with Faraday's law because when they brake, they have what's called regenerative braking. As they brake, they have magnets that are going to move, and as the magnets move, they actually create an electrical current because they induce a voltage as the magnets move past different types of metal. So one of the ways that a hybrid car recharges its battery is by braking and having those magnets induce a voltage, which is going to create a current of electricity that can be fed to the battery. And last but not least is a metal detector. As you walk through a metal detector, all right, and there's a current of electricity going through, and you have something metal on you, like keys or that metal moving past the actual detector creates a disturbance in the magnetic field. That flux in the magnetic field is going to create a change in current or an induced voltage, and because of that, the machine or instrument will pick up on that and buzz. Then you get to go over to the, I believe they're called the TSA, and they're going to get that wand and frisk you and make you take your shoes off, etc. Obviously, it's all for a good reason. It's for extra safety, but Faraday's law is exploited there. The last thing that may be very, very important is our electricity that we get in our house is made from gigantic generators. Now, generators are basically these huge coils of wire, and you're going to have magnets around the outside of them. And when we boil water from like burning coal or natural gas or however, that steam is going to turn a turbine, and that turbine is going to spin our magnets or our coil. By spinning our magnets around the coil or a coil in and out of the magnets, etc., you're going to induce a voltage which creates a current. So we literally create electricity by spinning and having magnets and coiled wire interact to create that induced voltage. Without that, we wouldn't have electricity in our home. So thanks a lot, Michael Faraday. Life is pretty convenient because of you, and that simple idea that a magnet in and out of a coil of wire can create a voltage, which can create current of electricity. Thanks for listening, Physics fam. Good luck. Try out some math problems in the upcoming assignments, and let me know how you're doing.